Our next speaker, Gerald Jackson. He's had about 15 years at Fermi National Accelerator Lab, and then he decided to go entrepreneurial and is now trying to make antimatter commercializate, make money at it.
And we have some years there's been a profit, some years there haven't. So this is a picture of me in my previous life as an accelerator physicist. The green magnet I'm pretending to hold up there is a 2-mile accelerator that we built. That was the last major accelerator project in the United States that was completed in the late 1990s. And that accelerator, just to give you an example of how costs and energy can come down tremendously by just thinking outside the box a little bit. This bottom accelerator down here, the conventional one, that costs $300 million to make. It's 2 miles in circumference. This one up here costs $12 million. Okay, and it had 100 times better vacuum and has about 12 times better stability. So there's a lot you could do by just thinking a little bit about a problem. So I've had 35 years accumulated experience working with either positrons or antiprotons. Just a little bit background. For the congressman that might be in the room, you might notice your colleague here. That's Congressman Bill Foster. He used to be a physicist at Fermilab. And when we got done with this project, he went off to Congress and I went off to do entrepreneurial stuff. So he's a good guy, very smart. It's a good thing we have people like that in Congress. So this is a plot of the luminosity or the performance criterion of the Tevatron Collider as a function of year. And you'll see this as a recurring theme. There's actually 2 exponentials in here. An early exponential, which in this case was a factor of 10 improvement every 5 years. And then this exponential, which was a factor of 10 improvement every 12 years. The change in slope is due to the scale, the civil constructions, the getting DOE permission to build things. I mean, once you get above a certain size scale, growth slows down, okay? And it's invariable. I've seen this on so many projects in my career. This is the 2-mile accelerator underground, about 30 feet underground. And so that's so what happens is 120 GeV protons are accelerated in the conventional accelerator, the $300 million accelerator. The proton beam then comes out and under this point right here hits a nickel target. And that produces the antiprotons. And the antiprotons then come into this triangular set of accelerators to get processed and cooled down to a usable beam. All the talks you've heard about how impossible antimatter is, how it takes 1,000 years to produce enough. The entire reason for that time scale is the constraints put on the production by the high energy physicists. They needed something called a small longitudinal emittance. That doesn't mean anything to you. What it means is that there was a certain parameter they required in order later on down the line to have colliding beams. When you remove that constraint, the production rate goes up tremendously, and that's basically the point of my talk. So back in 2000, between 2002 and 2005, at the same time John Slow was at NIAC doing his work with that plasma cell, we were there working on this propulsion system. And the basic idea is that you send just a thermal beam of antiprotons, or antihydrogen in this case. So just waft a cloud of antihydrogen onto a uranium sail. And what will happen is 99 or 98% of the time, the interaction of the antiproton with the surface uranium causes uranium fission. And so very simply, one fission daughter goes on average into the sail, one fission daughter goes out the back, you have thrust, you have momentum transfer. And the exhaust velocity is the fission daughter velocity. So that's at 4.4% of the speed of light. So you put in your log of mass initial over mass final, and you can get delta V's of 10% of the speed of light with just a factor of 10 ratio between the mass of the payload and the mass of the sail. So what we assumed is a 10 kilogram payload, and at the time we were severely criticized for being a factor of 100 too small in payload mass. So it's kind of funny now to hear about 1 gram payloads, right? But for a 10 kilogram scientific package, we calculated to get to Proxima Centauri, you needed the delta V required to get to Proxima Centauri was 17 grams of antimatter. So that's kind of the metric that I'm aiming at in this talk, is how do we produce that 17 grams of antimatter? So here's the nickel target that's used at Fermilab. This is, again, that conventional accelerator, and then my accelerator above there. And then these are the triangular machines that are used for cooling. So what we want to do is we want to go from 2 nanograms per year, which is what Fermilab produced when they shut off the source, the antiproton source. We want to get that up to 2 grams per year. That was the goal of this study that I just performed, and this was crowdfunded. So we raised $2,000, and that paid for all the work you're seeing presented here now. So what you need to do to get 9 orders of magnitude up is you need to improve the antiproton production, and then you have to figure out a way to accumulate the antimatter, and then how do you store that much antimatter? So the basic process is 2 colliding, or 1 proton beam going into a target, or 2 colliding proton beams. And the excess energy in the collisions creates a proton-antiproton pair. You separate off the antiproton, and that's what you use. At Fermilab, the ratio of production was 1 antiproton for every 10 to the 5th of protons on target. It turns out that if you go and reevaluate that, removing all the constraints and going with a thin target, this becomes, instead of 1 part 10 to the 5, it becomes 1%. So right away, you get 3 orders of magnitude just from removing that 1 constraint. So in this target, it's a thick nickel target, and about 1/3 of the protons interact, and 2/3 pass through and go to a dump and just generate heat. So that's the other disadvantage of this nickel target, is so much of the protons, you spend all this energy accelerating them, and then you're just dumping them and producing heat. It's a very inefficient process. Now, the proton beam, we said Fermilab was 120 GeV, and the reason for that is because this is the probability of producing an antiproton as a function of the incident energy of a proton beam on a target. And this is the 120 GeV right here. Threshold is 5.6 GeV. So if you had a 5G or 5.6 GeV beam, you could actually produce some antiprotons, but the probability of production is so low that it's not useful. And so that's why we always go to higher energies to produce them. So there was a paper back in the 1990s, I think it was 1994, that said, well, what if we go with a thin target? So we either put a thin target here, or we use a gas jet, a hydrogen gas jet going across the beam, or a thin foil, or a petting trap holding some sort of ion beam, ionized conglomerate of particles. And so you go through and you model this, and that certainly gives you the factor of 1,000 improvement plus some more. And then if you look at, well, what if I do a collider orientation? And so to get back to the same equivalent energy of Fermilab, which was 120 GeV proton beam on a target, you collide 1.9 GeV proton beams. And that gives you the exact same center of mass energy, and so you produce antiprotons at the same rate. Now, you don't really want to do this because the antiprotons come out isotropically and you can't do anything with them. So what you want to do is boost one of these beams a little bit higher in energy and one of the other one a little bit lower in energy, so you have a net boost to the reference frame, and now you've created a coherent beam coming out one end. So this is just an example. This has really nothing to do with the talk, but in the history of accelerator physics, we've seen a 10 to the 8th improvement in energy in accelerators over a little bit under 100 years, 75 years. And again, you see this same issue where the initial growth curve is very short. It's 6 years for every factor of 10. And then there's a knee, and you start seeing very slow growth of 25 years for every factor of 10. And this again has to do with scale of the project, the cost of the project, getting permission, signing treaties, all these other things, acquiring land, convincing people that they should leave their farms, all this other stuff. And so in looking through this and I realized that to get this 9-fold improvement that we need, 3-fold is free just from going to a thin target or colliding proton beams. And then the rest of it comes from the fact that I don't need to go up to the full 120 GeV proton beam if I'm colliding, and if I'm not dumping them all, and if I don't have electrons decelerating the protons going through a target, I can reuse the same beams going through each other repeatedly until they finally do interact. So you pick up a huge amount of efficiency. And so very early on, we realized that it's very feasible for us to do, to get this 10 to the 9th improvement. A lot of the studies that one would want to do to remove technical risk and to show this works can actually be done today parasitically at Fermilab. They're still running most of the accelerators, so we could just sneak time in and actually most of the users wouldn't even know we're doing that, just scraping off 1% of their beam, and they wouldn't even notice. And we could do a lot of work on this. So next, accumulation. So this is the conventional ways that you have at CERN. They have a cloud of positrons, a cloud of antiprotons, and they interact them. Okay, the problem is that you have to have just the right energy of collision in order to get a bound state, okay? And that phase space, the probability of getting that is very low. And so what you really need is you need a way of, you need a third body to couple into the interaction, okay? And because the CERN production rate, even at their peak, was only 1% of the antiproton production rate of Fermilab, their clouds are so sparse that it's very infrequently do they get a 3-body interaction. So the idea is that you have to do something different, okay? And so we know that ion bombardment grows mass on a substrate. That's a well-defined thing. You see that all the time. And we know that you can do electron bombardment to charge an object. So the basic idea is do the same thing with antimatter. So now let's say you have a massive antimatter here in the middle. You have some antinuclei going back and forth, and you have some positrons going back and forth. They have kinetic energy. They hit that particle in the middle, the mass in the middle, and they deposit their kinetic energy into that, and you get neutralized antimatter, and it's a very robust, very fast process. You don't have any of the formation problems you have at CERN. The problem with what they're doing at CERN and what people have thought of in the past is that hydrogen and helium, you have to be at cryogenic temperatures, and even then they have a terrible vapor pressure. And so for storage and for accumulation, when you have, let's say, a hydrogen snowflake in the middle of that trap, and you're bringing in antiprotons and positrons, you're vaporizing it, okay? It's just not a very good element to do this sort of accumulation process. And so if you look at the various other elements, and now we're not talking about antimatter, but regular matter, here are the melting points for beryllium, or lithium, beryllium, boron, and then carbon's off the scale here. So, and the melting points, and these are their vapor pressures as a function of temperature. And so clearly you want to be over here with something like carbon or boron and not with hydrogen or helium. And so we did a study where we assumed accumulation rate of 10 grams per year. So more than the 2 grams per year that was kind of the point of this study, because we wanted to see if there were any hidden problems. So as you're accumulating, and assuming that this levitated mass is spherical, its radius grows, which means its surface area grows. And so the mechanism by which it's giving up that heat is black body radiation. You put in the natural emissivities for those surfaces, and what you get is you get a plot here, which is the maximum kinetic energy, assuming both the positrons and the antinuclei have the same kinetic energy. And so this is the maximum kinetic energy you can continuously deposit into that body as a function of time within a growth period. So you're starting with a 1 hour accumulation, 1 hour mass worth of accumulation, and you're accumulating for a year. So this is a log plot, and this is a log plot. So even for lithium, your maximum kinetic energy of your two beams is less than an EV. It's not practical. So right away you can just knock off lithium. And so it turns out that, again, boron or carbon are the best candidates if you were to perform this sort of accumulation process. So the problem now is, well, that's okay. How do you get anti-lithium carbon? I mean, how do you do that? Okay. And the first thing that had to be solved is, where in the heck are you getting antineutrons from? Okay, how are you making these antineutrons? Making a free antineutron is pointless because you have no way of grabbing onto it, because the production energy, any of the processes you could come up with, that antineutron has so much energy that there's no way to constrain it, confine it, steer it, anything. So what you do is you want to form it as a bound state with an antiproton. So you want to form antideuteron. And nature has been very kind to us. It turns out that 80% of the time, if you take a 70 MeV antiproton beam and collide it with a 70 MeV antiproton beam, you get an antideuteron. And you get a witness pi minus, a pi meson out also. So now you have an antideuteron beam, okay? And the question is, well, what do you do with that? And so here is the antimatter factory. So think of this as an automobile assembly line. So this stage right here is you're putting the engine into a chassis. Here you're putting on an alternator. Here you're putting on a tire, and so on. So all of these processes are occurring in parallel in real time with small amounts of antimatter always being passed from one stage to the next. And so here's your antiproton beam and antiproton beam, and you get your antideuteron. You collide the antideuteron with an antiproton, and you get antihelium-3. The antihelium-3 with antideuteron, you get antihelium-4, so on to get to beryllium-7. Beryllium-7 decays to lithium-7. You then collide lithium-7 with the helium-4, you get boron-10. You get up to carbon-11, that decays in 21 minutes to boron-11. You then collide boron-11 with antihelium-4, and you get carbon-14. Okay, so we now have a stable version of carbon-14. So we have, so the overall mass efficiency in this is 73%. So 73% of the antimatter mass, the antiprotons that you start with, end up as anticarbon. This is, in principle, theoretically, a very efficient process. Now, when you build real accelerators with real vacuums and so on, it's not going to be anywhere near that good, but it's still going to be probably on the order of 50% or so. So that's still pretty good. Okay, we were just complaining, we were throwing between ourselves 9 orders of magnitude. Now we're only worrying about a factor 2. Okay, so that's a big victory. Okay. So, I was cheating though. For those of you who might have noticed, where did that first little lump of antimatter come from that I was colliding into? Okay, so the solution to this problem of where does that initial mass comes from, the solution is in the sourdough bread production. Okay, so if you go out to San Francisco and you taste some of their wonderful sourdough bread, they have the same yeast culture from 100 years ago. And all they do is they keep adding flour and water. They grow their culture, take a bit off, grow that, make bread. And they keep growing that, keep doing that over and over again. So what you do is you do the same thing with antimatter. So you use a rotate, there's something with penning traps called a rotating wall technique. And so what you do is you spin this thing up, so now all the deposition of the particles is on the end, and you're growing a whisker. So instead of a sphere, you now have a whisker. And then periodically as needed, you use a laser, you cleave off a little bit of that, and you use that for your next starter culture. So the only real issue is making the first few, probably we said it was about 10 to 100 nanograms, is what you would need to start in order to start building this up. So you have a problem with producing neutralized antimatter just once. And then once you've created that mass, you can just reuse it again, the same as you reuse the yeast culture. Okay. See what else. Okay. So what we're doing. So the other issue is you have to levitate this neutral mass, and you want to store it also so that it, obviously doesn't touch the walls while it's going across the interstellar void. And so there are two issues. One is levitation during that accumulation process, and the other is the levitation during that long voyage, and they're kind of different problems. So in terms of, where am I? So it turns out the solution is diamagnetism. And most people don't realize that most materials actually are magnetic, but it's called diamagnetism. And so what it is, if you have a mass of, let's say carbon, is actually the most diamagnetic of all the elements. And you apply a magnetic field through it, it tries to reduce the magnitude of the magnetic field within the material. And so what that does is it allows that mass to be, it causes the mass to seek a magnetic minimum. And so unlike electrostatics or any paramagnet material, you could actually have a three-dimensional magnetostatic confinement in all dimensions. So it's a stable confinement process. And so you see that here with water is diamagnetic. So you see a frog levitated. And here you see a piece of graphite being levitated by some permanent magnets. So during accumulation, the problem is if you're applying a magnetic field to levitate that mass up, that same magnetic field is causing your anti-nucleus beam and your positron beam to curl and to miss the mass. So what you want to do is pulse it. So you want the anti-nuclei, the positrons to come in a pulse fashion, and between pulses, you want to apply a fast magnetic field to bump up the mass. And so you just, it's like juggling. You're just hitting it periodically to keep it up. So in order to produce that fast magnetic field that's doing the levitation, you need a TEM waveguide, and you propagate a current pulse down here, and you get a quadrupole magnetic field with a field minimum in the middle. And so now gravity is causing it to push down against this force, and so you have your lump is off axis, but it's still being levitated. And then longitudinally along the wires, we're using a Helmholtz coil configuration where the two coils are separated too far, more than they should be to get a flat magnetic field, so that we have a dip in the middle, and that provides the confinement longitudinally. The other way you can do it is to sag these wires so that it forms a little bit of a curve, and then the particle will want to stay at the bottom of the sag. So those are the two ways you can do it. And this experiment that you see right here, this was built this summer by a mechanical engineering student from Princeton who worked for me. And then, so for long-term storage, first of all, carbon is nice because it has a very low vapor pressure, And it turns out that carbon-14 has a 5,700-year half-life. So it is, I mean, regular carbon-14 is a beta emitter with a relatively low energy beta kinetic energy. Now, anti-carbon is a positron emitter. Most of those positrons, the range is so low that most of the positrons annihilate within the body of the lump, okay, that you're storing. So what happens is that basically all you're doing is heating up that lump. And if you go through the whole black body radiation calculation and so on, it says that the equilibrium temperature that is going to be maintained by that radioactive decay is slightly above liquid nitrogen, which these neodymium magnets are perfectly fine running at those temperatures. So we already have, and this is, for those of you who went to the poster session last night, this was my demonstration of antimatter carbon storage. So this is a pencil lead, and it's being levitated up in the middle of the air. Now, for anti-carbon, you would have vacuum and so on. It'd be a little bit more to it, but this is basically all you need. So this talk was just an introduction, and I haven't really proven to you the plausibility of all this. That requires a detailed design report and an experimental roadmap that we're currently working on, but given that we have day jobs and we're not funded to any real extent, right now the time it's going to take to do this, to write these reports, is probably measured in years. So really what we really need is some external financial support so we could make this our day job. Get all the science, so the point is, or the goal is, to write down all the physics, get all the experimental evidence down, build the experimental roadmap so this could be reviewed by a scientific review committee, and we could actually get on the road to making this a reality.
That was great. Coming from a high energy physics background, I appreciate someone who actually knows what they're doing here, so thank you. So a couple of quick questions. First, I do see an interesting path forward to lower mass confinement, which has always been the bane of any antimatter approaches. And it'd be interesting to push forward on this and see if we can actually do it. If you look at the current estimates for the mass of confinement, secondary mass of confinement, versus the mass of antimatter that you're confining, if you have some estimate, I'd appreciate that. The other question is on the efficiency of conversion of sort of electrical energy into the equivalent antimatter annihilation energy. So if you have an estimate for that, it's clearly, if you're going at 120 GeV on the input beam and you're getting 1 GeV out effectively in an antiproton, the efficiency is, even at 100% efficiency for electricity into accelerators, which of course is not true, it would be less than 1%. But I'm just curious if you have a good estimate for the number.
Well, that's part of the reason for the design report, is to actually, instead of waving my hands, actually doing real numbers. Now, it turns out that, there's a lot of history that goes into this, but basically, we don't have an energy issue as a species because there's infinite solar power. On the scale of what we're using, I think the entire human consumption of power can be serviced by a 30 kilometer by 30 kilometer array of solar cells, okay? It's not that much of an issue. The problem is delivery of power, okay, and nighttime, and the fact that we don't have a storage mechanism as a species. The beauty of this is you can produce the antimatter during daylight hours, and you can have a dedicated solar field out in the middle of some desert. And so you're not impacting the rest of society by consuming all electricity. So now it's just a capital cost issue, okay? It's not really a societal issue. And the initial estimate we've had is, I think it was 10 kilometers by 10 kilometers solar cells would provide enough power to do what we want to do.
Which is doing what? Producing a gram per year? Or
2 grams per year.
2 grams.
And then now for this example, you do, you run that for 8 years and you get enough for, presumed mission. Now, this idea that the energy efficiency is a big deal. It's not really, because if you just look at nuclear bombs and nuclear power, have you ever tried to go through and calculate how much energy went into all the mass separation, all the processes that went into making that enriched nuclear fuel, right? It's just incredibly inefficient, but there was a need for it, so they did it.